Hello there, and welcome to Simple Sleepy Science Channel. Right now, as you listen to these words, you're swimming, not in water, but in something just as real, just as vital. An invisible ocean flows around you, through you, keeping you alive with every moment that passes. We call it air, but it's so much more than empty space. It's a river of gases, a stream of molecules, all moving in patterns we rarely stop to notice. And like any river, it has a rhythm, a balance, a way of flowing that's been perfected over billions of years. If you're enjoying this journey into the wonders of science, please hit that like button and subscribe so you don't miss more amazing stories tomorrow. And I'd love to know, where are you watching from right now? What time is it there? Drop a comment and let's build this community of curious minds together. Tonight, we drift into something extraordinary, something that touches every living thing on this planet, but remains completely invisible to our eyes. We're going to explore the atmosphere, but not as a layer of gases in a textbook. Instead, picture it as a living, breathing river that wraps around our world, flowing from the peaks of mountains to the depths of valleys, from the heat of deserts to the cold of polar ice. This river has currents, it has tides, it moves and swirls and dances in ways that scientists are still trying to fully understand. And the most remarkable thing about it is what it carries. Nitrogen makes up most of it, providing a gentle cushion. But mixed in with that nitrogen is something precious: oxygen, the molecule that keeps us alive. Every breath you take right now pulls oxygen from this invisible river into your lungs. Your blood grabs it, carries it to every cell in your body, uses it to create energy, to power your thoughts, your movements, your heartbeat. Then you release carbon dioxide back into the river and it flows away, cycling through the system. But here's what makes this truly amazing. You're not alone in this river. Every person on Earth is breathing from it right now. Every animal, from the smallest ant to the largest whale, is pulling oxygen from this same flowing stream. Birds flying overhead are swimming through it. Fish in the ocean are filtering it from water. Trees and plants are both taking from it and giving to it in a constant exchange that never stops. This invisible river has been flowing for billions of years, long before humans existed, long before dinosaurs walked the earth. It's ancient, it's reliable, it's always been there, so consistent that we never think about it. We just breathe, trusting that the next breath will come, that the oxygen will be there waiting. Scientists who study this river have tools that can measure it precisely. They can count the molecules, track how the balance shifts with seasons, monitor how oxygen levels change from place to place. And because they've been measuring for decades, they know what normal looks like. They know the rhythm, the pattern, the way this river should flow. The measurements show something beautiful. Despite all the breathing happening every second, despite all the oxygen being consumed, the levels stay steady. Why? Because the river is constantly being replenished. Plants on land and tiny organisms in the ocean work day and night, taking in carbon dioxide and releasing fresh oxygen back into the flow. It's a cycle, a loop, a system that balances itself. But once, not too long ago, something almost broke that pattern. For a brief time, the invisible river started to change in ways it shouldn't. The rhythm faltered, the balance shifted, and scientists around the world noticed their instruments showing something they'd never seen before. This is the story of the day Earth almost forgot how to breathe. High on a mountain in Hawaii, there's a research station that most people have never heard of. It sits above the clouds, far from cities and factories, breathing the cleanest air on Earth. The scientists who work there have one simple job. They measure the air. Every day, every hour, instruments pull in samples and count the molecules. Oxygen, carbon dioxide, nitrogen. The same routine, day after day, year after year. It sounds boring, maybe, but these measurements matter more than most people realize. They're taking Earth's pulse, checking its vital signs, watching for changes that could tell us something important about our planet. On one particular morning, a scientist named Dr. Chen arrived at the station like always. She made her coffee, checked the instruments, looked at the overnight data, and something caught her eye. The oxygen reading was slightly lower than it should be. Not dramatically, just a fraction of a percent. The kind of number that could easily be a glitch, a faulty sensor, a bit of dust on the equipment. She ran the calibration tests. Everything checked out. The instruments were working perfectly. She looked at the previous day's data. Normal. The day before that. Normal. But this morning, the number had dropped. Dr. Chen wasn't the panicking type. She'd seen odd readings before. Weather patterns could cause small fluctuations. Volcanic eruptions could temporarily change the mix of gases. She made a note in her log and decided to watch it for a few more days. The next morning, the number was lower still. Then lower again the day after that. 3 days in a row, each measurement showing less oxygen than the one before. Now, Dr. Chen felt a prickle of concern. She picked up the phone and called a colleague at another station in Alaska. Had they noticed anything unusual? Her colleague pulled up their data. Yes, actually, they'd seen a small drop too. Same pattern. Started 3 days ago. They'd assumed it was a local thing, maybe something to do with the ocean currents nearby. Dr. Chen hung up and stared at her screen. 2 stations, thousands of miles apart, both showing the same change at the same time. That wasn't a glitch. That wasn't local weather. She started calling more stations. Antarctica, Norway, Australia, New Zealand. One by one, the answers came back. Yes, we've seen it. Our numbers dropped too. Same timeline, same pattern. By the end of the day, Dr. Chen had contacted 17 monitoring stations around the world. Every single one reported the same thing. Oxygen levels were dropping. Not quickly, not dangerously yet, but measurably, consistently, everywhere. She sat back in her chair and felt something she'd never felt before in 20 years of taking measurements. Fear, not panic, but a deep, cold understanding that something was happening to Earth's atmosphere. Something global. Something that didn't care about borders or oceans or hemispheres. Whatever was affecting the planet's breathing, it was happening everywhere at once. The invisible river that had flowed steadily for billions of years was changing, and nobody knew why. To understand what was happening, we need to meet some characters in this story that most people have never seen. They don't have faces or voices. They're smaller than the period at the end of this sentence, but they might be the most important living things on Earth. They're called phytoplankton, and they drift in the ocean by the trillions. If you scooped up a cup of seawater, you'd be holding thousands of them. Under a microscope, they look like tiny jewels. Some are round like marbles. Others have spikes or tails. They come in shapes that seem almost designed by an artist. These tiny organisms do something remarkable. They float near the surface of the ocean where sunlight reaches, and they use that light to do the same thing plants do on land. They take in carbon dioxide from the water and release oxygen. One tiny phytoplankton doesn't make much oxygen, but when you have trillions upon trillions of them spread across all the oceans of the world, working every single day, they produce something incredible. More than half the oxygen you're breathing right now came from them. Not from forests, not from grasslands or gardens. From these microscopic organisms drifting in the sea. Every other breath you take exists because of phytoplankton. Think about that for a moment. Something so small you can't see it without special equipment is responsible for keeping half the planet breathing. They've been doing this job for billions of years, long before the first plants ever grew on land. They're the original oxygen makers, the ancient workers that transformed Earth's atmosphere from something poisonous to something that could support complex life. And they're still working, right now, in the Pacific Ocean, in the Atlantic, in the Indian Ocean, in every sea and stretch of salt water on Earth. Phytoplankton are soaking up sunlight and releasing oxygen. It's happening continuously, endlessly, a process that never stops as long as the sun keeps shining on the water. Different types of phytoplankton live in different parts of the ocean. Some prefer warm tropical waters. Others thrive in the cold seas near the poles. They bloom in huge numbers when conditions are right, turning the water slightly green or blue, visible even from space. These blooms are beautiful, but more than that, they're planetary life support systems in action. Fish depend on phytoplankton, not directly, but through a chain. Tiny animals eat the phytoplankton. Small fish eat those tiny animals. Bigger fish eat the small fish. Whales filter massive amounts of water to catch the smallest creatures. Everything in the ocean connects back to these microscopic organisms at the foundation. But their most important job isn't feeding fish. It's making oxygen. Scientists have studied them for decades, measuring how much they produce, tracking their populations, understanding what they need to survive. And what they've learned is simple. Phytoplankton are tough, but they're also sensitive. They need the right conditions, the right temperature, the right amount of nutrients, the right balance. And as Dr. Chen was making her phone calls, as monitoring stations around the world confirmed that oxygen levels were dropping, marine biologists were starting to notice something happening to the phytoplankton. Something that would explain everything. Picture a glass of ice water sitting on a table. As the ice melts, the water stays cold. But once all the ice is gone, the water starts to warm up. The ocean works in a similar way, only much slower and more complex. Temperature matters to everything living in it. Phytoplankton are like Goldilocks creatures. They need conditions to be just right. Too cold, and their tiny bodies slow down. Their chemical reactions happen less efficiently. They still produce oxygen, but not as much, too warm, and they face different problems. The heat stresses them. Their delicate machinery starts to malfunction. For several weeks before Dr. Chen noticed the oxygen drop, something had been happening in the oceans. Temperatures had been climbing. Not everywhere, not dramatically. Just certain areas, scattered across the globe, had gotten warmer than usual. A degree here, 2 degrees there. The kind of change that wouldn't feel like much if you dipped your hand in the water, but meant everything to organisms that live their entire lives in that water. Scientists track ocean temperatures using satellites and floating sensors. They'd noticed the warming, logged it in their data, watched it spread. Warm patches appeared in the Pacific. The Atlantic saw rising temperatures in specific zones. Parts of the Indian Ocean heated up. These warm spots weren't connected by geography, but they were all happening at roughly the same time. In those warmer waters, phytoplankton populations started to struggle. The heat put them under stress. They still performed photosynthesis, still took in carbon dioxide and released oxygen, but not as efficiently. Some types of phytoplankton couldn't handle the warmth at all. Their numbers dropped. Others survived, but produced less. Individual phytoplankton are tiny, so one struggling organism means nothing. 1,000 struggling means nothing. Even 1,000,000 barely registers. But when you're talking about trillions of them spread across multiple ocean zones, all getting stressed at the same time, suddenly the numbers start to matter. Less oxygen produced in the Pacific, less in the Atlantic, less in the Indian Ocean. Each warm zone meant fewer active phytoplankton doing their job. And because oceans cover more than 70% of Earth's surface, changes there affect the entire planet's atmosphere. The oxygen they normally released into the water would bubble up to the surface and enter the air. That process was still happening, but at a reduced rate, like a factory that normally runs at full capacity suddenly operating at 80%. Still working, still producing, but not enough to keep up with demand. Marine biologists studying phytoplankton noticed the changes in their samples. Smaller bloom sizes, different species ratios, signs of heat stress in the microscopic structures. They documented it carefully, published their findings, shared data with colleagues. But nobody had connected it to the atmospheric oxygen measurements yet. That connection would come soon. Dr. Chen and her fellow atmospheric scientists were looking at air. Marine biologists were looking at water. Both groups were seeing pieces of the same puzzle, but neither had stepped back far enough to see how the pieces fit together. The warming waters kept spreading. More zones heated up. More phytoplankton populations felt the stress. And with each passing day, the oxygen production dropped a little more. The invisible river was getting thinner, its flow weakening, as the tiny organisms responsible for filling it struggled in what had become just slightly too warm for comfort. Everything in the ocean is connected. When one thing changes, it pulls on everything else, like tugging a single thread in a massive web. The stressed phytoplankton weren't just producing less oxygen. They were starting a chain reaction that would ripple through the entire marine ecosystem. Tiny animals called zooplankton spend their lives eating phytoplankton. They're barely bigger than the organisms they consume, drifting through the water, filtering millions of phytoplankton through their bodies. But when phytoplankton populations drop, zooplankton have less food. Some starve. Others produce fewer offspring. Their numbers start to decline. Small fish eat zooplankton. Schools of them, millions strong, swimming through the ocean with their mouths open, catching these tiny animals by the thousands. When zooplankton populations drop, the small fish struggle. They have to swim farther to find enough food. They grow more slowly. Some don't survive. Medium fish eat small fish. Bigger fish eat medium fish. Seabirds dive down to catch fish near the surface. Seals and dolphins hunt in deeper water. Whales filter enormous amounts of water to catch the smallest creatures. Every level of the ocean's food chain depends on the level below it. This is how ecosystems work. Remove one piece and everything else shifts. But here's what matters for our story. All those animals, from the smallest zooplankton to the largest whale, are breathing. They're taking oxygen from the water. And that oxygen came from phytoplankton. So we have a double problem developing. The phytoplankton are stressed and producing less oxygen. But they're also less abundant, which means less food for everything else. The ecosystem is being squeezed from both sides. Marine biologists in different parts of the world started reporting unusual observations. Fish populations behaving strangely, seabird colonies where fewer chicks were surviving, dolphins spotted in areas they normally avoided, presumably searching for better hunting grounds. None of these observations seemed connected at first, just scattered data points from researchers doing their work. But back in Hawaii, Dr. Chen was starting to piece things together. She'd been reading everything she could find about what might cause a global oxygen drop. One paper caught her attention. It was about phytoplankton sensitivity to temperature. She read about the warm water zones. She looked at maps showing where the warming was happening. Then she pulled up her atmospheric data and overlaid it with the ocean temperature maps. The correlation wasn't perfect, but it was there. Areas with the most warming showed slightly bigger drops in oxygen levels downwind. The atmosphere above warm ocean zones looked different from areas above cooler water. She called a marine biologist she'd met at a conference years ago. They talked for 2 hours, comparing data, sharing observations. By the end of the call, they both understood what was happening. The ocean's oxygen makers were struggling. The ripple effects were spreading through the ecosystem. And the atmosphere was showing the results. But understanding the problem didn't solve it. The warm zones weren't cooling down. If anything, they seemed to be expanding. More areas of ocean were heating up. More phytoplankton populations were getting stressed. The chain reaction was still building, still spreading, and nobody knew where it would stop or how bad it would get before something changed. While scientists focused on the oceans, something else was happening on land. The forests, those massive stretches of green covering continents, were facing their own struggles. And forests matter just as much as phytoplankton when it comes to the oxygen we breathe. Walk into a forest on a sunny day and you can almost feel it working. The leaves above you are busy, soaking up sunlight, pulling carbon dioxide from the air, releasing oxygen back out. Billions of leaves on millions of trees, all doing this same process simultaneously. It's the other half of Earth's oxygen production system. But here's something many people don't realize. Trees breathe too. Not the way we do, but they take in oxygen at night when photosynthesis stops. They use it to power their own life processes. Just like any living thing, during the day, they flip the switch. They take in much more carbon dioxide than oxygen and release far more oxygen than they consume. The net result over a full day is positive. They're oxygen makers. That balance matters. A healthy tree in good conditions produces plenty of oxygen, but a stressed tree produces less. And that spring, forests around the world were dealing with unusual stress. In the Amazon, rainfall patterns had shifted. Some areas got too much rain, flooding root systems. Other areas got too little, forcing trees to conserve water by closing the tiny pores in their leaves. Those same pores are where carbon dioxide enters and oxygen exits. Close them too much and photosynthesis slows down. Northern forests in Canada and Russia faced late frosts that damaged new growth. The trees survived, but had to spend energy recovering instead of growing. Less growth meant less photosynthesis. Less photosynthesis meant less oxygen production. Forests in Southeast Asia dealt with heat waves that pushed temperatures beyond what many trees could handle comfortably. Like the phytoplankton in warm water, these trees could still function, but not at peak efficiency. None of these individual problems were catastrophic. Forests are resilient. They've survived worse conditions throughout history. But the timing mattered. All of these stresses were happening at once, spread across different forests on different continents, all during the same few weeks when the ocean's phytoplankton was struggling. Forest researchers documented these conditions in their regular monitoring. They measured tree growth, tracked leaf health, noted the unusual weather. They published updates in scientific journals. But like the marine biologists, they didn't immediately connect their observations to the oxygen measurements Dr. Chen was tracking. Trees don't produce oxygen as quickly as phytoplankton do per unit of living material. But there are so many trees covering so much land that their total contribution equals roughly the other half of Earth's oxygen production. When forests slow down, even slightly, the atmosphere notices. So now, both systems were underperforming at the same time. The ocean's phytoplankton, stressed by warm water. The land's forests, stressed by unusual weather. Together, they'd normally keep the invisible river flowing at a steady rate. But stressed systems don't work at full capacity. The oxygen levels kept dropping. Dr. Chen watched her instruments with growing concern. Other monitoring stations reported the same steady decline. And somewhere in the back of her mind, a question started forming. If both the ocean and the forests were struggling, how long could this continue before everyone started feeling the effects? Dr. Chen stopped sleeping well. Every morning she'd arrive at the station on the mountain, make her coffee, and stare at the screen showing overnight data. Every morning the number was lower than the day before. Not by much, tiny fractions, but always down, never up. She started keeping a graph on the wall, a simple line chart showing oxygen levels over time. For years, that line had been almost perfectly flat, with only minor natural variations. But now, it looked like a ski slope, downward, steady, relentless. Her colleagues at other stations shared the same experience. They'd email each other late at night, comparing numbers, double-checking calculations, hoping someone would find an error in the measurements. But there were no errors. The instruments were working perfectly. The drop was real. Think of it like a bank account. Every day, billions of people and animals withdraw oxygen by breathing. Plants and phytoplankton deposit oxygen through photosynthesis. For Earth's entire history, the deposits had always matched or exceeded the withdrawals. The account stayed balanced, but now the deposits were getting smaller while the withdrawals stayed the same. The account was still in good shape. There was plenty of oxygen in the atmosphere, but the trend worried scientists. If it continued, eventually the balance would tip into dangerous territory. Dr. Chen did the math. At the current rate of decline, oxygen levels would stay safe for months, maybe longer, but that assumed the rate stayed constant. What if it accelerated? What if more ocean zones warmed up? What if forest stresses got worse? She wasn't the only one thinking about this. Research stations around the world had become hubs of worried activity. Scientists who normally worked independently were now in constant communication. They set up video calls, shared data in real time, created collaborative documents tracking every measurement. In Norway, a researcher noticed that the drop seemed slightly worse during daylight hours. In Australia, someone else confirmed the same pattern. This made sense. During the day, when photosynthesis should be replenishing oxygen most actively, the levels were still dropping. It meant the production had fallen significantly below normal. The scientists faced a difficult decision. They had data showing a clear problem, but no immediate danger. Oxygen levels were still well within safe ranges. Most people wouldn't notice any difference yet, but the trend was unmistakable. Something was wrong with Earth's breathing system. Should they go public? Alert governments? Risk causing panic over a situation that might stabilize on its own? Or should they stay quiet, keep monitoring, and hope the problem resolved itself naturally? Dr. Chen attended video conferences with senior scientists from a dozen countries. They debated for hours. Some argued for caution. Others insisted that the world needed to know. The discussions got heated at times. Everyone felt the weight of the decision. Finally, they reached a consensus. They would share their findings, not with dramatic announcements or alarming press releases, but through proper scientific channels. They'd publish their data, brief government officials, and let the information spread through appropriate networks. Dr. Chen helped write the summary. She chose her words carefully, presenting facts without exaggeration. The oxygen levels were dropping. Both ocean and land systems showed signs of stress. The situation required attention and monitoring. They didn't know if it would get worse or stabilize. She hit send on the email to her government contact. Then she sat back and waited to see what would happen when the world learned that the air itself was changing. Before we continue with what happened next, let's talk about what it means when oxygen levels drop. Most people have never thought about this because oxygen levels don't normally change in any noticeable way during a human lifetime. If you've ever climbed a high mountain or flown in an airplane, you've experienced lower oxygen. The air gets thinner the higher you go. At the top of Mount Everest, there's about 1/3 as much oxygen as at sea level. Climbers struggle. Every step requires enormous effort. Their bodies aren't getting enough oxygen to function normally. But that's extreme altitude. The oxygen drop scientists were measuring was nothing like that. It was subtle, fractions of a percent, the kind of change that sensitive instruments could detect, but human bodies couldn't really feel yet. Yet is the important word. Our bodies are remarkably good at adapting to small changes. People live at different altitudes all over the world, and their bodies adjust. But adaptation takes time. A sudden change, even a small one, affects us differently than a gradual one we grow up with. The drop scientists measured was happening at sea level, everywhere. It was like the entire planet had climbed 100 feet higher in elevation. Not much. You wouldn't notice it walking upstairs or going for a jog. But your body would be working slightly harder to get the same amount of oxygen into your bloodstream. For most healthy people, this meant nothing obvious. Maybe feeling a bit more tired than usual. Maybe needing an extra moment to catch your breath after exercise. The kind of things you might blame on poor sleep, or stress, or getting older. But for people with breathing problems, heart conditions, or other health issues, even small changes mattered. Doctors in several countries started noticing a slight uptick in patients complaining about fatigue and breathlessness. Nothing dramatic, just a small increase in the background noise of normal medical complaints. Animals were different. They couldn't tell anyone how they felt, but researchers noticed behavioral changes. Birds flying at slightly lower altitudes. Some fish species moving to different depths. Wild animals spending more time resting and less time active. Subtle shifts that could have many explanations, but the timing matched the oxygen decline. The really concerning part wasn't where things stood currently. The atmosphere still had plenty of oxygen. We were nowhere near dangerous levels, but scientists understood trends. They knew how to read graphs, and every projection showed that if the decline continued at the current rate, within a few months, people would start feeling it more noticeably. Within 6 months, it might affect work productivity and athletic performance. Within a year, it could impact human health more seriously, especially for vulnerable populations. And if it accelerated, rather than staying constant, those timelines would compress. Dr. Chen thought about this often. She'd stand outside the research station, breathing the thin mountain air she was used to, and imagine that same air getting thinner still. She thought about cities at sea level, where billions of people lived, all breathing air that was slowly, imperceptibly, getting less rich in the molecule that powered their lives. The measurements continued. The line on her graph kept trending downward, and everyone watching those numbers wondered the same thing. Where would it stop? Would it stop? Or would Earth's invisible river keep getting thinner until everyone, everywhere, felt the difference? Scientists don't just measure and watch, they also predict. They build computer models that try to forecast what might happen next, based on current conditions. It's similar to weather forecasting, but instead of predicting rain or sunshine, they were trying to predict the future of Earth's atmosphere. Teams at research centers around the world fed their computers everything they knew: ocean temperatures, forest health data, phytoplankton populations, historical oxygen levels, seasonal patterns. They added information about weather systems, ocean currents, even upcoming changes in sunlight as seasons shifted. The computers crunched the numbers, running thousands of simulations. Each simulation was like a possible future, a different way things might unfold based on slight variations in conditions. Some showed the oxygen levels stabilizing within a few weeks. Others showed continued decline for months. A few showed scenarios where the drop accelerated. Dr. Chen attended video conferences where scientists presented their models. Each research group had slightly different results because they weighted factors differently or used different baseline assumptions. But certain patterns appeared across most models. If ocean temperatures started cooling, even by a degree or two, phytoplankton would likely recover quickly. These organisms bounced back fast when conditions improved. Similarly, if the unusual weather patterns affecting forests normalized, trees would resume full photosynthesis within weeks. But there was a problem. The models couldn't predict when or if those improvements would happen. Weather and ocean and temperatures follow patterns, but those patterns aren't perfectly predictable. The computers could say what would happen if temperatures cooled, but they couldn't say with certainty when that cooling would begin. Some models included human intervention. What if countries reduced air pollution significantly? What if large-scale ocean cooling projects were attempted? What if massive tree planting campaigns began immediately? These scenarios showed positive effects, but they'd take time to make a difference. Weeks at minimum, more likely months. The uncertainty frustrated everyone. Scientists like clear answers. They like being able to say this will happen at this time for this reason. But Earth systems are incredibly complex. Everything affects everything else in ways we don't fully understand. The oceans influence the weather. The weather affects the forests. The forests change how much carbon dioxide gets absorbed. That affects ocean chemistry. Round and round in loops within loops. Dr. Chen looked at dozens of different model outputs. The range of possibilities was wide. Best case, oxygen levels would bottom out soon and start recovering within a month. Worst case, they'd continue dropping for half a year or more, reaching levels that would cause noticeable health impacts globally. Most models fell somewhere in between. A continued decline for several more weeks, then a leveling off, then a slow recovery once conditions improved. Not catastrophic, but not comfortable either. The scientists shared these projections with government officials. They explained the uncertainties, the possibilities, the range of outcomes, and they faced a question that had no easy answer. Do you tell the public about a crisis that might resolve itself? Do you risk causing worry and panic over projections that might not come true? Or do you stay quiet and risk being blamed later if things get worse? Different countries made different choices. But the information was out there now. And slowly, quietly, the word began to spread that something was happening to the air we breathe. The first article appeared in a scientific journal. Dry language, lots of graphs, the kind of paper that normally only researchers would read. But this one got noticed. A science journalist wrote a summary for a major news website. Then another picked it up. Then another. Within days, headlines started appearing. They ranged from measured to alarming. Some simply stated the facts. Atmospheric oxygen levels showing unusual decline. Others went dramatic. Is Earth running out of air? The world holds its breath as scientists warn of oxygen crisis. People read these headlines on their phones during breakfast, on computers at work, on tablets before bed. and they reacted in different ways. Some panicked. They imagined suffocating, gasping for air, the atmosphere disappearing like water draining from a tub. They bought oxygen tanks and air purifiers, even though those wouldn't help with this kind of problem. They posted worried messages on social media, asking if they should prepare for the worst. Others dismissed it entirely. The air seemed fine. They felt normal. Scientists had been wrong before, hadn't they? This was probably exaggerated. Just another scare story that would blow over in a few days. Many people fell somewhere in between, concerned but not panicking, curious about what it meant, trying to understand if they should change anything about their daily lives. Government officials held press conferences. They brought scientists along to explain the situation using simple terms. Yes, oxygen levels were dropping. No, there was no immediate danger. The situation was being monitored closely. People should stay calm and continue their normal activities. But calm is hard to maintain when you're talking about the air itself changing. Some countries accelerated existing environmental plans. They announced new protections for oceans and forests. They fast-tracked regulations to reduce pollution. Not because these actions would fix the immediate oxygen problem, but because they addressed the broader health of Earth's systems. Communities organized tree planting events. Thousands of people showed up to dig holes and plant seedlings. It felt good to do something, even if a few thousand trees wouldn't solve a planetary problem. The act itself mattered. People taking action, caring about the invisible river they'd always taken for granted. Companies made announcements too. Some promised to reduce their carbon footprint. Others pledged to protect marine habitats. A few were probably just taking advantage of the moment for good publicity. But others seemed genuinely motivated to help. Scientists found themselves in an unusual position. Normally, they worked quietly, published papers, attended conferences. Now, they were getting calls from news organizations, requests for interviews, invitations to speak to government committees. They tried to be accurate and honest, without either downplaying the problem or making it sound worse than it was. Dr. Chen did several interviews from her station in Hawaii. She spoke carefully, explaining that the situation was serious, but not immediately dangerous. That Earth's systems were resilient, but also delicate. That we were witnessing something unprecedented, a real-time change in atmospheric chemistry that normally only happened over thousands of years. The world was paying attention now. Millions of people suddenly aware of something they'd never thought about before. The oxygen in the air wasn't infinite or guaranteed. It was produced by living systems that needed protection and care. And those living systems were still struggling, still stressed, while everyone watched and wondered what would happen next. While headlines grabbed attention and governments made announcements, real change started happening in small ways, spread across millions of individual choices and local actions. In coastal cities, fishing regulations tightened. Areas that had been open to commercial fishing were suddenly protected. The goal was to give marine ecosystems a chance to stabilize, to reduce any additional stress on systems already struggling. Fishermen complained about lost income, but many also understood. They'd seen changes in the ocean themselves, noticed fish behaving differently. countries with coastlines created new marine protected zones. Ships were routed away from sensitive areas. Restrictions on ocean dumping became stricter. None of these actions would instantly fix the phytoplankton problem, but they reduced other pressures on ocean health. On land, forest protection accelerated. Brazil paused logging permits in parts of the Amazon. Indonesia strengthened enforcement against illegal forest clearing. Canada and Russia increased monitoring of their northern forests. Again, these weren't immediate solutions, but they helped systems already under stress. Individual people made changes too. Car use dropped in many cities as people chose to walk, bike, or use public transit more often. It wasn't just about reducing pollution. It felt like doing something, contributing in whatever small way possible to helping Earth's systems recover. Community gardens sprouted up in urban areas. People planted trees in their yards. Schools organized environmental projects. A neighborhood in Tokyo planted rooftop gardens on dozens of buildings. A village in Kenya started a massive tree planting initiative. A city in Brazil created new green spaces in previously concrete areas. Companies changed practices more quickly than usual. Some installed better air filtration systems in factories. Others modified processes to reduce emissions. The motivation was partly public pressure, partly genuine concern, partly just good business sense in a world suddenly focused on atmospheric health. Scientists noted all of this with cautious optimism. None of these individual actions would fix the oxygen problem by themselves. The drop was caused by natural systems under stress, and only those systems recovering would truly solve it. But reducing additional stress helped. Every bit of pollution not released meant one less thing for forests and phytoplankton to cope with. The social shift was interesting too. People talked about breathing differently now. They noticed the air, stepped outside, and thought about where oxygen came from, looked at trees and oceans with new appreciation. Something invisible had become visible through its potential absence. Parents explained to children about phytoplankton and forests. Teachers incorporated the oxygen situation into lessons. It became a moment of collective learning. Billions of people simultaneously getting a crash course in how Earth's life support systems actually worked. And slowly, very slowly, the impact of all these changes started to accumulate. Less pollution meant slightly healthier forests. Protected ocean zones gave marine life breathing room. It wasn't enough to reverse the oxygen drop on its own, but it helped stabilize things, prevented them from getting worse as quickly as they might have. Dr. Chen watched her measurements with intense focus. The decline was still happening, but she thought maybe, just maybe, the rate had slowed slightly. It was hard to be sure. The change was tiny, but after weeks of watching numbers go down, even a slowing of that descent felt like hope. The question remained whether these human efforts, combined with Earth's own resilience, would be enough to turn things around before the oxygen levels dropped too far. Nature has been through worse, much worse. Ice ages that covered continents, volcanic eruptions that darkened the sky for years, asteroid impacts that wiped out most life on Earth. And through it all, the basic systems that produce oxygen kept working, adapting, surviving, recovering. marine biologists monitoring the warm ocean zones started noticing something encouraging. In a few areas where temperatures had dropped even by half a degree, phytoplankton populations responded almost immediately. Within days, their numbers increased. Within a week, oxygen production measurements from those zones showed improvement. It was remarkable how quickly they bounced back. These microscopic organisms had no intelligence, no awareness, but they had something more valuable: resilience built through billions of years of evolution. They'd survived every catastrophe Earth had thrown at them. Warm water was stressful, but not deadly, and when conditions improved even slightly, they recovered fast. Forest researchers observed similar patterns. Trees that had been stressed by unusual weather showed new growth when conditions normalized. A forest in northern Canada that had been hit by late frost started producing healthy leaves again as temperatures warmed to normal spring levels. The Amazon areas that had been too dry received rainfall, and the trees responded within weeks. This resilience made sense. When you thought about it, Earth's climate has always varied. Hot years and cold years, wet seasons and droughts, ocean temperatures that rise and fall. Life evolved to handle variation. These systems had backup capacity, the ability to ramp production up or down based on conditions. Think of it like your own body. When you get sick, your immune system responds. You might feel terrible for a few days, but then you recover. Your body heals itself when given the chance. Earth's systems worked similarly. The stress had pushed them below normal function, but they weren't broken. They just needed conditions to improve. Scientists studying soil made an unexpected discovery during this time. They'd been taking samples from various locations, trying to understand every possible source of oxygen. And they found something surprising. Certain types of bacteria living in soil produced oxygen as a byproduct of their life processes. This wasn't news exactly. Scientists knew some soil bacteria produced oxygen. But what they hadn't measured accurately was how much. It turned out to be more significant than previous estimates suggested. Not enough to replace forests or phytoplankton, but a meaningful contribution to the total oxygen budget. Even more interesting, these bacteria seemed to be producing more oxygen than usual. The stress conditions affecting forests and oceans had created changes in soil chemistry. Those changes favored certain bacterial populations. They multiplied, and in doing so, increased their collective oxygen output. It was like Earth had a backup system nobody knew about. Or rather, a backup system scientists hadn't fully measured. When the main oxygen producers struggled, this hidden workforce picked up some of the slack. Dr. Chen read the soil bacteria papers with fascination. It reminded her that Earth's systems were far more complex than any model could capture. There were layers upon layers of interactions, feedback loops, and balancing mechanisms that humanity barely understood. The planet had been regulating its own atmosphere for billions of years without human help. It had systems within systems, backups and redundancies, ways of maintaining balance that operated automatically. Maybe, just maybe, those systems would be enough to carry Earth through this crisis, given enough time and a little help from reduced human pressure. It happened on a Tuesday morning. Dr. Chen arrived at her station, made her coffee as usual, sat down at her computer. She pulled up the overnight oxygen measurements, expecting to see the same downward trend she'd been watching for weeks. The number had stabilized. Not gone up yet, but it hadn't gone down either. For the first time in over a month, the line on her graph was flat instead of sloping downward. She stared at the screen, checked the instruments, ran diagnostics. Everything was working correctly. She looked at data from the previous week, confirming the trend. Yes, the decline had been slowing over the past few days, and now it had stopped. Her hands shook slightly as she called the station in Alaska. They confirmed it. Their measurements showed the same thing. A plateau. The oxygen levels had stopped dropping. Over the next few hours, reports came in from monitoring stations around the world. Norway, Australia, Antarctica, New Zealand. Everyone was seeing it. The decline had halted. But why? What had changed? Meteorologists provided part of the answer. Several major weather systems had shifted in the past week. A high-pressure system in the Pacific had moved, bringing cooler air over warm ocean zones. Wind patterns in the Atlantic had changed, mixing cooler deep water up to the surface. Nothing dramatic or unusual in terms of weather, just the normal movement of Earth's atmospheric and oceanic systems. But the timing mattered enormously. Those cooler temperatures arrived in multiple ocean zones simultaneously. Water temperatures dropped by a degree here, 2 degrees there. Not cold, just closer to normal seasonal ranges. And the phytoplankton responded. Marine biologists taking samples saw population increases in areas that had been struggling. The microscopic organisms were blooming again, soaking up sunlight, releasing oxygen, doing what they'd done for billions of years. On land, spring weather was finally settling into more typical patterns. The unusual cold snaps had ended. Rainfall was normalizing. Forests that had been stressed found themselves in better conditions. Trees resumed full photosynthesis. The oxygen production from land systems increased back toward normal levels. Scientists looked at the soil bacteria data too. While they were still producing more oxygen than usual, that contribution became less critical as the main systems recovered. It was like a backup generator that could shut down once main power was restored. Dr. Chen updated her graph. The line had been diving downward for weeks. Now it had flattened. The oxygen level wasn't back to where it started, but it had stopped falling. That was huge. It meant the planet's breathing systems had caught up with the demand. Production and consumption were back in balance. She allowed herself to feel cautiously optimistic. The crisis wasn't over. Oxygen levels were still lower than normal, but the trend had changed. Instead of watching things get worse every day, they were watching them stabilize. Other scientists shared her careful optimism. They'd seen how quickly phytoplankton could recover when conditions improved. They'd observed trees bouncing back from stress. If the favorable conditions continued, if ocean temperatures stayed stable, if weather patterns remained normal, then oxygen production should gradually climb back to previous levels. The measurements over the next few days would be critical. One day of stability didn't guarantee a trend, but it was the first good news since this whole situation began, and everyone monitoring Earth's breath held onto that small spark of hope. Wednesday, the line ticked upward, just slightly, a tiny fraction of a percent, but upward. Thursday, up again, a little more this time. Friday, still climbing. Dr. Chen watched with the kind of attention people usually reserve for watching a loved one recover from illness. Every data point mattered. Every small increase felt like a victory. She wasn't celebrating yet. She'd learned not to trust short-term fluctuations. But the pattern was encouraging. By the end of the week, oxygen levels had climbed back halfway to where they'd been before the decline started. The recovery was happening faster than the decline had occurred. When systems tipped back toward favorable conditions, life responded quickly. Plaka. The ocean temperature data told the story clearly. Multiple zones that had been warmer than normal were now cooling. Not because of anything humans did, but because weather patterns had shifted. Earth's climate system was doing what it always did, cycling through variations, redistributing heat, moving energy around the globe. Those cooler waters made all the difference for phytoplankton. Marine biologists reported blooms appearing in areas that had been struggling. The microscopic organisms were multiplying rapidly now, making up for lost time. Satellite images showed patches of ocean turning slightly greener as phytoplankton populations exploded. This was normal for them. Phytoplankton populations naturally fluctuated with seasons and conditions. They could boom and crash and boom again. Their fast reproduction allowed them to respond quickly when opportunities arose. Cool water and sunshine were all they needed, and now they had both. Forest monitoring showed similar positive trends. Trees were putting out new growth. Leaf cover was expanding. Photosynthesis measurements indicated that forests were back to producing oxygen at normal rates. In some areas, they seemed to be producing even more than normal, as if making up for the period of reduced activity. The soil bacteria that had ramped up production were still working hard. Their contribution continued, adding to the overall recovery. Scientists were still studying why their populations had increased, but the effect was measurable and helpful. But here's what the scientists learned from watching this recovery. Earth's oxygen levels had always been more variable than they'd realized. The monitoring systems before this crisis hadn't been comprehensive enough to catch all the natural fluctuations. Oxygen levels probably rose and fell in small amounts all the time, responding to seasonal changes, weather patterns, ocean conditions. What made this event unusual was the magnitude and the combination of factors. Ocean warming and forest stress happening simultaneously across multiple regions. That pushed the variation beyond normal ranges. But even then, the planet's systems hadn't broken. They'd just been temporarily overwhelmed. Now, those systems were recovering, not because humans had fixed anything fundamental, though reducing pollution and protecting habitats probably helped prevent things from getting worse. The recovery was happening because Earth's natural regulatory systems were doing their job. Weather patterns had shifted on their own timeline. Ocean temperatures were normalizing through natural processes. Forests were responding to better conditions. And life, resilient and ancient, was bouncing back. Dr. Chen felt something she hadn't felt in weeks. Relief. Deep, profound relief. The crisis wasn't completely over. Oxygen levels still needed to climb higher, but the turning point had arrived. Earth had caught its breath. the invisible river was flowing stronger again, fed by trillions of tiny organisms in the ocean and billions of trees on land, all working together in a system that had sustained life for eons and would continue long into the future. Once the immediate crisis passed, scientists had time to step back and understand what had actually happened. They gathered data from hundreds of sources, compared timelines, built detailed analyses. The picture that emerged was both simpler and more complex than anyone expected. Earth's oxygen levels had never been as stable as textbooks suggested. Looking back through historical data, with new attention to detail, researchers found small fluctuations that had been dismissed as measurement errors or local variations. But they weren't errors. They were real changes, just too small for anyone to worry about before. Oxygen levels naturally varied within a range, going slightly up and down with seasons, with major weather patterns, with ocean conditions. Most years, these variations stayed small enough that nobody noticed. The atmosphere is vast and oxygen abundant, so small changes got lost in the noise. What made this event different was the alignment of multiple stresses happening at the same time. Ocean temperatures warming in several zones simultaneously. Forest stress from unusual weather across different continents. These weren't connected by any single cause. They were separate events that just happened to overlap in timing. Think of it like traffic. Normally, rush hour is busy but manageable. But if rush hour coincides with an accident, a sporting event letting out, and construction closing a lane, suddenly you have gridlock. No single factor caused the problem. It was the combination that overwhelmed the system. Earth's oxygen production system had been in a similar situation. Each individual stress, taken alone, would have caused a small dip that recovered quickly. But all of them together pushed the system harder than usual. Production dropped below consumption. The balance tipped. Scientists also learned something important about feedback loops. As oxygen levels dropped slightly, it created small atmospheric changes that affected weather patterns. Those weather pattern changes influenced ocean temperatures and rainfall, which affected oxygen production, which changed the atmosphere, round and round. These feedback loops could work both ways. During the decline, they amplified the problem slightly, but during recovery, they helped speed things up. Better conditions led to more oxygen production, which improved atmospheric conditions, which helped maintain those better conditions. Human activity played a role too, though not the way people initially thought. Pollution and habitat destruction hadn't directly caused this event. The timing was wrong for that, but they had created background conditions that made Earth's systems more vulnerable to natural variations. Think of it like immunity. A healthy person can fight off a minor infection easily. A person already stressed and run down might struggle with the same infection. Earth's systems were similar. Centuries of human impact had stressed them enough that natural variations pushed harder than they would have otherwise. The good news was that this worked in reverse too. When people reduced pollution and protected habitats during the crisis, it didn't solve the immediate oxygen problem, but it gave the systems more capacity to recover once conditions improved naturally. This was the key lesson. Earth's atmosphere wasn't a static thing that stayed perfectly balanced unless something catastrophic happened. It was dynamic, constantly adjusting. responding to countless inputs. Usually, those adjustments were small and self-correcting, but occasionally, when multiple factors aligned poorly, the adjustments could be larger and more noticeable. The planet had systems to handle this, resilient life forms that could boom when conditions allowed, feedback loops that helped stabilize things, natural variations in weather and ocean temperatures that eventually cycled back toward average. These systems had kept Earth habitable for billions of years through far worse conditions than a few weeks of reduced oxygen production. The crisis changed how humanity monitored Earth. Before, atmospheric measurements were scattered and somewhat limited. A few dozen stations around the world taking regular samples. Satellite observations that measured broad patterns but missed local details. It had seemed sufficient because nothing major ever changed. Now, governments understood that sufficient wasn't good enough. They needed to know what was happening in real time, with precision everywhere. Within months of the oxygen recovery, countries collaborated on building a comprehensive monitoring network. New stations went up on every continent and many islands. Floating sensors were deployed across the oceans, measuring both atmospheric and water conditions. Satellites got upgraded instruments that could track oxygen levels, phytoplankton blooms, and forest health simultaneously. The data from all these sources fed into shared databases. Scientists anywhere in the world could access the information. No more delayed reports or isolated measurements. The system provided a continuous, global picture of Earth's breathing. It was like upgrading from taking your temperature once a year to wearing a fitness tracker that monitors your heart rate, breathing, and activity constantly. Problems could be spotted early, trends identified quickly, changes understood in context. The monitoring revealed patterns nobody had seen before. Seasonal variations in oxygen that followed the growth cycles of northern forests. Weekly fluctuations tied to weather systems. Even daily changes as the sun rose and set, affecting photosynthesis rates around the globe. Marine monitoring became especially sophisticated. Sensors tracked not just phytoplankton populations, but also water temperature, nutrient levels, and acidity. This let scientists understand what conditions helped or hindered the microscopic oxygen producers. They learned which species thrived in which environments, how quickly they could recover from stress, what early warning signs looked like when populations started to struggle. Forest monitoring got similar upgrades. Satellite imagery combined with ground sensors could track tree health across entire regions. Scientists could see stress developing before it became critical. Unusual leaf color indicating drought stress. Growth patterns showing nutrient deficiencies. Early signs of disease or pest problems. This comprehensive monitoring served as an early warning system. If conditions started aligning poorly again, if ocean zones began warming while forests faced unusual weather, scientists would know immediately. They could alert governments, suggest interventions, track whether actions were helping. But the monitoring did more than watch for problems. It also deepened human understanding of Earth's systems. The data revealed connections that had only been theoretical before. How ocean currents influenced weather patterns hundreds of miles inland. How forest fires in one region affected atmospheric chemistry globally. How everything truly was connected to everything else. Dr. Chen helped design parts of the new monitoring network. She traveled to other countries, training scientists on best practices, sharing lessons learned from the crisis. The Hawaiian station, where she worked, became a hub in the global system. Its pristine mountaintop location, perfect for baseline atmospheric measurements. She sometimes thought about how close they'd come to missing the oxygen decline entirely. If the old monitoring system had been slightly less sensitive, they might not have caught it until people were feeling serious effects. The new system made that near impossible. Earth's vital signs were now being watched carefully, constantly, by thousands of instruments and hundreds of scientists working together. It wasn't just about oxygen anymore. The comprehensive approach monitored everything that mattered for planetary health. And if something started going wrong again, humanity would know quickly enough to respond before small problems became large crises. The crisis changed people in ways that had nothing to do with science or policy. It shifted something fundamental in how millions of individuals thought about the world around them. A teacher in Japan started taking her students outside every morning for what she called breathing meditation. They'd stand quietly, breathe deeply, and she'd remind them that half the oxygen filling their lungs came from the ocean. The kids would look at the distant water with new understanding. Something invisible had become precious. A businessman in New York found himself noticing trees on his commute. Before the oxygen event, they'd been background scenery, part of the urban landscape he barely registered. Now he saw them differently. Each tree was working, producing oxygen, contributing to the air he breathed. He started supporting local tree planting initiatives, donating money to protect forests he'd never visit. A grandmother, Brazil, told her grandchildren stories about the tiny organisms in the ocean, describing them like heroes in an adventure tale. The children drew pictures of phytoplankton, imagined them as magical creatures keeping the world alive. They learned to care about parts of nature they couldn't see or touch. These individual shifts happened everywhere. People who'd never thought about environmental issues suddenly paid attention, not from fear or guilt, but from appreciation. The oxygen crisis had made the invisible visible. It showed how connected everything was, how dependent human life remained on natural systems. Community gardens became more popular, not just for growing food, but for the satisfaction of nurturing life that produced oxygen. People talked about their plants differently, acknowledging them as partners in breathing. The act of gardening took on new meaning. Beaches saw more volunteer cleanups, not because people suddenly cared more about plastic pollution in an abstract sense, but because they understood the ocean as a living system that needed protection. Those microscopic phytoplankton deserved clean water. The connection felt personal now. Parents made different choices about transportation. Walking and biking increased not just to reduce pollution, but because people wanted to participate in taking care of air quality. Each small decision felt like contributing to something important, maintaining the invisible river that sustained everyone. Schools changed curricula to include more about Earth's systems. Children learned about the oxygen cycle, the way previous generations had learned about math and history. Understanding how the planet worked became as fundamental as reading or writing. These kids would grow up with knowledge that their parents had only recently gained during a crisis. The language people used changed too. They talked about breathing differently, acknowledging it as a gift rather than a given. Phrases appeared in conversations that would have seemed strange before. Thank the trees, appreciate the ocean, respect the air. Not religious language, but something similar, a recognition of dependence and gratitude. This wasn't universal. Some people went back to their old habits once the crisis passed, forgetting the brief moment of awareness. But many didn't. The experience had shifted their perspective permanently. They'd glimpsed how fragile the balance was, how much life depended on systems that usually operated invisibly. And this collective shift in consciousness spread across millions of people making small changes and thinking differently, created a foundation for larger changes. When governments proposed stronger environmental protections, public support was higher than before. When companies advertised their sustainability efforts, people paid attention and rewarded those commitments with loyalty. The oxygen crisis hadn't just tested Earth's resilience. It had awakened something in human awareness, a recognition that we're not separate from nature, but participants in it, dependent on systems we must help protect. The oxygen crisis answered some questions, but created many more. Scientists found themselves with years of new research directions, mysteries to solve, connections to explore. The event had revealed how much humanity still didn't understand about its own planet. Research teams focused on phytoplankton with renewed intensity. They wanted to map every species, understand their specific temperature tolerances, learn how different types responded to various stresses. The goal was to predict future problems before they became critical. If scientists could identify which phytoplankton populations were most vulnerable and where they lived, early interventions might be possible. One team discovered that certain phytoplankton species were much more temperature sensitive than others. These could serve as early warning indicators. If their populations dropped in specific ocean zones, it might signal that conditions were shifting toward another oxygen event. The monitoring network started tracking these indicator species specially. Forest researchers pursued similar goals on land. They studied how different tree species responded to various stresses: drought, heat, cold, pests, disease. Some trees were remarkably resilient, others were fragile. Understanding these differences helped predict which forests might struggle if conditions changed and which would remain stable. The soil bacteria discovery opened an entirely new field of research. Scientists had underestimated the oxygen contribution from soil microorganisms. Now, teams around the world collected soil samples, cultured bacteria, measured their oxygen production under different conditions. The findings suggested that soil health mattered much more for atmospheric oxygen than anyone had realized. This led to new appreciation for agricultural practices that protected soil. Farmers learned that healthy soil with diverse microbial communities didn't just grow better crops, it also contributed to the air everyone breathed. Some farming methods that had been promoted mainly for soil health now had an additional benefit recognized. Climate researchers incorporated oxygen dynamics into their models. Before, they'd focused mainly on carbon dioxide and temperature. Now, they understood that oxygen levels needed attention too. The models became more sophisticated, able to simulate how different climate scenarios might affect Earth's breathing systems. The mathematical models still couldn't predict everything, Earth systems were too complex, with too many variables interacting in ways that weren't fully understood. But the models improved with each new piece of data. They got better at identifying risk factors, at suggesting which conditions might lead to problems. International scientific collaboration strengthened. The oxygen crisis had demonstrated that planetary problems couldn't be solved by individual countries or research groups. The new monitoring network was just one example. Scientists also shared research data more openly, coordinated studies across borders, published findings in accessible formats. Young scientists entering the field were inspired by the event. Applications to marine biology and atmospheric science programs increased. A generation of researchers was emerging who'd witnessed a planetary crisis and wanted to dedicate their careers to understanding and protecting Earth systems. Dr. Chen mentored some of these young scientists. She saw their enthusiasm and remembered her own early career before she understood how vulnerable the atmosphere could be. These new researchers started with knowledge she'd only gained through crisis. They approached their work with urgency balanced by hope. The questions they asked were fundamental. How resilient were Earth's life support systems really? What were the true limits? How much stress could the planet handle before reaching genuine tipping points? And most importantly, how could humanity live in ways that supported rather than undermined the systems that sustained all life? The research continued, the data accumulated, and slowly, carefully, understanding deepened. The oxygen crisis became a reference point, a before and after moment in how humanity approached planetary health. Scientists and governments watched for signs that conditions might align poorly again, ready to respond more quickly than before. The monitoring network provided constant reassurance. Every day, data flowed in from thousands of sensors. Scientists analyzed patterns, looking for anything unusual. Most days showed normal variations. Oxygen levels fluctuated within expected ranges. Phytoplankton populations bloomed and declined with seasons. Forests cycled through growth and dormancy. But sometimes, warning signs appeared. An ocean zone would start warming faster than normal. A forest region would show early stress from drought. The monitoring system would flag these situations immediately, and scientists would pay close attention. In most cases, conditions self-corrected before becoming serious. The warm ocean zone would cool as weather patterns shifted. Rain would arrive to relieve the drought-stressed forests, natural variation working as it always had, problems arising and resolving within the planet's normal range of adjustment. But twice in the 3 years following the crisis, conditions started aligning in worrying ways. Both times, the early warning system gave governments time to act. The first instance involved ocean temperatures rising in multiple zones simultaneously, similar to what had triggered the original crisis. Countries responded by temporarily expanding marine protected areas, reducing shipping traffic in sensitive regions, and accelerating pollution controls. The actions weren't dramatic, but they reduced additional stress on systems already dealing with warm water. When temperatures normalized a few weeks later, phytoplankton populations had remained stable enough that oxygen production barely dropped. The second instance involved widespread forest stress from unusual weather patterns across several continents. Governments implemented emergency fire prevention measures, provided support for forest management, and temporarily restricted logging in vulnerable areas. Again, these actions didn't solve the weather problem, but they prevented additional stress from compounding natural difficulties. Both times, oxygen levels showed minor dips, but nothing approaching the scale of the original crisis. The combination of better monitoring, quicker response, and reduced background stress from improved environmental practices seemed to be working. Earth's systems could handle normal stresses more easily when they weren't already burdened by excessive pollution and habitat destruction. International agreements on ocean and forest protection strengthened. Countries that had dragged their feet on environmental issues before now participated more actively. The oxygen crisis had made the stakes clear. Everyone breathed the same air. Protecting the systems that produced it wasn't just environmental idealism, it was practical necessity. Climate agreements incorporated oxygen monitoring as a key metric. Negotiators discussed not just reducing carbon emissions, but protecting the natural systems that produced oxygen. Forest preservation and ocean health became central topics rather than side issues. This vigilance became routine. The heightened awareness didn't fade as the crisis receded into memory. Instead, it became embedded in how society functioned. Just as checking weather forecasts or monitoring economic indicators had become normal. Watching Earth's vital signs joined the list of things civilization did routinely. Dr. Chen sometimes reflected on how close they'd come to a much worse outcome. If the natural systems had been less resilient, if the weather hadn't shifted when it did, if human response had been slower or less coordinated. But those what-ifs didn't haunt her. Instead, they reinforced her commitment to vigilance. The planet had shown it could recover, but it had also shown that its balance wasn't guaranteed. Vigilance wasn't paranoia, it was care, attention to something precious that deserved protection. We started this journey together by imagining the atmosphere as an invisible river flowing around our planet. Now, as we reach the end of this story, that image has deepened. The river isn't just flowing around us, we're part of it. Every breath we take connects us to that ancient current. Think about what happens when you breathe in. Oxygen molecules enter your lungs. Some of those molecules were released by a tree in your neighborhood. Others came from phytoplankton drifting in the Pacific Ocean. Still others were produced by bacteria in soil halfway around the world. Each breath is a gift from life forms you'll never see, working constantly to keep the invisible river flowing. And when you breathe out, you release carbon dioxide. That molecule might be absorbed by a plant in someone's garden tomorrow, or captured by phytoplankton in the Indian Ocean next week, or taken in by a tree in the Amazon next month. Your breath becomes part of the cycle, feeding the systems that will produce oxygen for someone else. This isn't poetic metaphor. It's literal truth. The oxygen you're breathing right now is billions of years old, cycled through countless living things, processed and reprocessed by Earth's systems over time spans we can barely imagine. You're participating in something ancient and enormous with every breath. The oxygen crisis taught humanity to see this connection. For a brief time, the invisible became visible through the possibility of its absence. People understood, perhaps for the first time, that breathing isn't a solo act. It's collaborative, it's planetary. we learned that Earth's systems are both resilient and fragile. Resilient because they've survived billions of years and countless disasters. Fragile because they depend on balances that can be disrupted when multiple stresses align. The planet can heal itself, but it needs conditions that allow healing. We learned that everything connects. Ocean temperatures affect forest health. Forest health affects atmospheric chemistry. Atmospheric chemistry affects weather patterns. Weather patterns affect ocean temperatures. Round and round in loops within loops, each part influencing all the others. And we learned that humanity's role matters. Not as controllers or masters of Earth's systems, but as participants who can either add stress or reduce it. The choice to protect forests and oceans, to reduce pollution, to pay attention, these choices affect the invisible river we all depend on. The story of the day Earth almost forgot how to breathe isn't really finished. It continues every day as scientists monitor, as forests grow, as phytoplankton bloom, as soil bacteria work in darkness, all contributing to the ancient process of keeping the atmosphere rich in oxygen. And it continues with you, right now, breathing, participating in Earth's oldest rhythm, connected through the air to every living thing on the planet, past and present and future. If you've enjoyed this journey through science and wonder, please take a moment to like this video and subscribe to our channel. We'll be back tomorrow with more stories that help you see the world differently. The next time you take a deep breath, maybe you'll remember. You're not just filling your lungs. You're participating in a planetary dance billions of years old, touching the work of countless organisms, connected through the invisible river to everything alive. Sleep well.